We've got a real treat coming up now. Arun Ghosh from AT&T will be giving our next presentation. And you can think of this presentation as the introduction to the AT&T and that will be held in the Capitol Room, there just beyond the mezzanine. So this presentation is a 20-minute throat clearing before this demo, where he can give us plenty of the background on. And like was mentioned last night and earlier this morning, this is the first demonstration of this technology in a public sense. So Arun, we're very happy to have you here, and take it away.
All right. Good morning, everybody, and thank you, Todd, for that introduction. Yes, this is a very exciting demonstration. As you said, this is the first time we are doing this. It's a demonstration based on a millimeter wave technology, as we all have come to understand is going to be a very central theme of 5G networks. Although, they're not the only theme, but they definitely represent a very big part of what 5G networks are all about. So today, one of the things that I wanted to talk about before we get to the demo and you see a live millimeter wave network and some cool technologies like multi-user MIMO and phased array-based hybrid beamforming, I want to talk a little bit about how do we deploy a millimeter wave network, particularly keeping in mind this whole V2X and vehicular technology requirements that we have. I think the two opening speakers today have summarized that the need of the kind of needs, bandwidth we are talking about is significantly more than what we have today. With the bandwidth, we are talking in excess of 100 megabits per second, perhaps even more than that. That's a number that we still, as a network deployed, we still don't know, but we know it is north of hundreds of megabits per second, and the kind of numbers I'm hearing there actually, quite frightening. But frightening maybe it's a challenge as well. So how do we go from having a network that today we have giant macro cells that deploy perhaps 20, 30 megahertz of spectrum on them, and then we deploy small cells where we need to offload the traffic, and a recent trend has been using unlicensed band as well. But all of that is quite far from where we need to take the network. And where we really need to take the network is we need to push bandwidth significantly higher. And how we are going to do this has been a challenge, for all of us. One thing we do understand that, if you look at pure spectral efficiency improvement, which is effectively how much more data can you push through your network without adding any more spectrum or adding any more infrastructure, those growths have been small. I mean, even twice in a factor of 2x or a factor of 3x in every generation of technology. And mind you, that comes at a cost of a tremendous amount of innovation. Things like massive MIMO, multi-user MIMO, those things are not trivial, but they still only lead you maybe 2x or 3x improvement in your overall system spectral efficiency. So that really has been the motivation why for a long time the industry has been moving towards millimeter wave. And the basic benefit, the simplest, is that we have a lot more spectrum. Instead of, tens of megahertz of spectrum, you're talking about gigahertz of spectrum. You're talking about 3 gigahertz of spectrum in the 37 to 40 gigahertz of spectrum. We're talking about upwards of 6 gigahertz of spectrum. So the amount of spectrum is huge, but it's not easy to use. And, one of the things that you will see is the main problem in millimeter wave is really your noise bandwidth. It's a bit of a misnomer that millimeter wave, propagation is bad, and with phased arrays and everything, we can actually completely overcome all the propagation challenges. The biggest challenge that still remains in millimeter wave is that you have PAs that have very poor efficiency. So when you run a PA with about 5% to 8% efficiency on a system bandwidth that is 500 megahertz wide, you're essentially very noise limited. And that is really reflected if you look at what happens to your cell edge spectral efficiency as you start pulling out the cell side, or the intersite distance from something like 100 meters to 300 meters. The cell edge literally tanks. And that is essentially because you are in a noise limited system. So if your desire is to use something like 500 megahertz of spectrum and you want to deliver 100 megabits per second. These simulations and modelings based on the currently well-accepted propagation models is roughly about 200 meters is the maximum distance you can put cell sites, and maybe even less. Maybe even less if you want not just enhanced mobile broadband. If you want real high bandwidth autonomous vehicular applications, you're probably looking at 100-meter cell site separation. So what does that mean? What is a 100-meter cell site separation? So that what you have in the top view is a picture of downtown Austin, and those red arrows are about 250 meters wide. So roughly a city block is about 200 to 250 meters in downtown Austin. Now you're talking about having intersite distance less than that, maybe 100 meters, maybe 120 meters. So you are talking about several small cell deployments every block to support this hundreds of megabits per second kind of a bandwidth for that we need for V2X and V2V kind of applications. So that's a challenge. How do we deploy this? We say it's downtown Austin, there's plenty of fiber, but as somebody who has been trying to build some of these test beds in a smaller scale, I know that the fiber may be feet away from you, but it's challenging to tap into. It's not always that easy to get to. And in many places, we don't even have that fiber. So downtown Austin might be a great idea, but once you start going out of them, once you start going on the highways don't have fiber embedded on them. So how do we handle deploying such a ultra dense network? And it's a challenge, and I don't think the answer is in one particular solution. Definitely a denser fiber deployment is going to be an essential part, but we think that there are a couple of other things that we want to essentially use, and one of the big theme of all of this is to move away from the traditional architecture that we know from cellular networks, where you have a base station and you have an end device and an end car, and you have a single link between the two of them. Now, it seems a bit of a waste in millimeter wave to design network that way. And the reason essentially is, if you look at how 4G networks really operate, you have a small amount of spectrum, which covers a very large area, hundreds of meters, several hundreds of meters, maybe even up to a kilometer. And you have a large number of devices that are a part of that network. So if you look at what we call as the system utilization is quite flat. It stays at a average, because you have it's a law of large numbers. So you have a large number of devices on the network. And the story with millimeter waves is exactly the opposite. It is very large bandwidth with very short distance coverage. So the system utilization ends up being extremely stochastic and very variable. So you end up deploying this network that you're not utilizing that much. And so the right way to do that seems that why don't I put backhaul and my access on the same system? And instead of designing a system which uses a single point and a single hop, I start utilizing multiple hops. Now, how many hops? We don't know. That's something that we have to study. But we do know that a single hop is not good enough. We need to deploy a multi-hop network. Now, how do we? Multi-hop networks have been around for a while. A lot of work has been done, in WNCG itself and many places around, and we have deployed those networks. But there are a few things that we might actually have to do differently, especially in millimeter wave. One of the main thing is that in millimeter wave, your point of association changes quite fast, and the main reason is because of events like blocking. So when you have blocking in millimeter wave, the transition periods are much faster in millimeter wave compared to traditional cellular frequencies, where once your base station starts to fade because something came in between, you turned a corner, the fading events take a longer time, and you can do essentially what we call a handover, which is a layer 3 handover, and the timings but those events happen is actually good enough. But that is not how things really happen in millimeter wave. The transitions are much more stochastic, much more short term. So you have to develop a multi-hop network where you can do very fast layer 2 switching, which is essentially a very, very different way of doing things. It's almost like Ethernet kind of a MAC level switching that you have to do in the case of millimeter wave, and which essentially means that if you look at a traditional network, you have a radio access network and a core network. That's typically how we divide our cellular networks today. We are talking about, so what this essentially means that you are designing a network with a completely RAN level mobility. You can handle the mobility within the radio access network itself. But we think we can do that. I think there are it's been done before, and there are certainly ways to handle that. So when we look at a dense, ultra dense network with integrated access and backhaul, the whole concept can be divided into three different parts. One which happens over larger time scale is essentially your topology management. This concept allows you to turn off access points, turn them off. Maybe you can even have mobile access points. Maybe even the cars themselves can be, relay points. So you have a need for the topology of the network to be fairly dynamic, and you can change associations. The relays can move themselves, essentially with the cars being, relay points themselves, which I think is a good solution for the highway case, where it might be very difficult to build in a lot of dense infrastructure, but you can use the vehicles themselves to be the hopping points on top of each other. And by the way, when you don't have a very dense deployment for high density of these vehicles, maybe you don't need so much autonomous driving. Maybe the person can drive. I'm assuming that there is a person in the car, right? Otherwise, why is the car driving by itself? So the topology management has to be dynamic. We need to, today, that's one of the fundamental problems of deploying small cells today, is that when you deploy a small cell, you have to manage it, you have to add it to your network. Once you do all those things, it becomes a usable entity. But what we want is something much more plug and play. You essentially, self-discoverable, access points, which is truly the way to go if you want the mobile relays to be a part of this. And then we have the other two events that happen over a longer time scale, which we call as, route selection / scheduling, and more of the dynamic frame structure. And, one of the things that we realize is that it's going to be quite challenging to operate full duplex systems with massive MIMO systems. So it might be simply easier to preserve the half duplex constraint, for massive MIMO millimeter wave systems, which means you have a fairly complex algorithm to run to figure out, what my frame structure should be, which ones are running in downlink, which ones are running in uplink, which ones are blanked out, so that you have to continuously do on a very, very short time scale. And typically the time scale is, in the case of 5G, it would be a subframe kind of a time frame, which is somewhere between a millisecond to significantly less than a millisecond, maybe 200 microseconds or 100 microseconds. So that's that's how we break this problem down into three different stages. This is one example of how you can build in topology discovery into the initial access mechanism itself. So when we say initial access is what happens when you turn on a device or a device enters a network. It does some kind of a time frequency synchronization. It does some kind of an identification of what the network is. And in the case of millimeter wave, you even have to do beam management and things like that. So we think we can build in topology discovery basically into the time management, into the initial access mechanism itself. And there are several ways to do that. To keep this transparent to the end devices and also transparent to the core network as well. I am running a bit short on time, so I will try to go forward. Maybe just one little slide to couch this problem in two different ways. So when we talk about multi-hop networks, there are really two ways to do this. One is a true mesh. And if you ask anybody who's a believer or an ardent fan of a multi-hop system, you will say this is really the way to go, because this is scalable, and what you can show that if you do if you let each node determine its determine the route of the packet, you can actually show that this is actually throughput optimal. But one of the problems that happens with a completely distributed scheduling is that the worst case is often bad. So doing any kind of quality of service or something for V2X may not be the best way. So you do want some degree of centralization so that you can also guarantee some kind of a worst case better than a minimum threshold. But the mesh architecture has, me being somebody who has to build the network, I'm also well aware of what standards are. And a true mesh is a little bit of a difficult challenge because we tried to do that for device-to-device communication, and we all saw what happened to it. So the and the difficulty that we face there is that if you want a true mesh, you have to define a new control channel and a new side link, which is going to be fairly challenging given where the standardization process are headed. So what we instead want to do and explore the possibilities is more of a hierarchical architecture where you don't need a new control channel. You essentially use the uplink downlink itself to create a hierarchical system. And you can show that, the route selection is not limited in any way in this case, but there are certain corner cases that you can actually not solve with this hierarchical problem, and it requires a little bit more planning. So I'll quickly skip to the overall summary, and I really welcome all of you to take a walk over and take a look at the demo. 5G millimeter waves are an essential part of a ultra-dense network, and given the kind of bandwidth and throughput we require, there's no doubt that this is really the way we have to go, and we are just getting started. Over the air, integrated access and backhaul, we believe is a very, very essential part of the overall end network architecture if you want to enable a truly ultra-dense network with multiple megabits or hundreds of megabits per second of bandwidth to support all kinds of use cases. So that is pretty much it, and thank you once again. If there are any questions.
Great, thank you, Arun. We've got time for one question. Gus, could you just go ahead and shout it out?
Yeah, that's a great question. In fact, I was just having that conversation with my friend Charlie Zhang of Samsung, and I think what you're talking about is more of a drone-based infrastructure, maybe. Yes, I think it is a very interesting problem. Although, one of the problems that we face in a drone-based system is that drones are extremely interference coupled because you have really no blocking. The blocking in millimeter wave is actually a blessing because you have to design the system for short distances anyway. So I think that is a very interesting use case and definitely something to look forward to. And, our friends in defense have gone that route, decades ahead of us. So I think there's some potential in that.
We'll see if our friends from Amazon do the same.
Yes.
Thank you again, Arun. And we'll now transition to the break. Let me give you a bit of logistics about the break so that you can be prepared for what you'll be seeing. Let's see here. This is a map of the area of the floor that we're on, the lecture hall on your left. The AT&T demonstration will happen in the Capitol Room, which is just across the so-called mezzanine area. And in the mezzanine area, there will be a series of presentations, student poster presentations from our wonderful students in the Wireless Network Communications Group. You'll want to mill around and take a look at these presentations and then drop by the AT&T demo. And I understand that many of you are not exactly the most social type. You maybe pretend to be outgoing only because your job demands it. And if you feel agoraphobia, go ahead and go across the breezeway to the actual Blanton Museum on the other side. They've given us free access to the museum. And you can see this wonderful exhibit. This is the famous Chinese artist Zhu Bing, his so-called book from the sky. And there are many of you here who speak Chinese. See if you can find the contradiction in this exhibit. All of the letters in the exhibit are something of a contradiction. We'll meet you back here at 10:40, and we'll ring the chimes 5 minutes in advance to let you know that the next speaker will be speaking at 10:40. We'll see you then.